Till now, what we have been looking at is the Fourier series in the interval minus pi to pi, where the period was 2 pi. Now, what happens if it is not from minus pi to pi, but some other interval, but period still being 2 pi? So here, the integral of a periodic function over any interval whose length is equal to the period is equal to the period. So here, integral from minus pi to pi f of x dx, this is what we have been looking at till now, is the same as, or rather this is the same as this. So integral from any arbitrary point on x to that point plus 2 pi of f of x dx. Their integrals will remain the same. Let's look at it with an example. Let's say I have a graph of sine x in the interval minus pi to pi. And when I take the integral, I get the areas under that curve. Now here in this case, these two areas cancel out. So the total area is 0. Now let's take another one. This is also sine x. The only thing is it is in a different interval, but the period is still the same, that is 2 pi. So if I take the integral, this is the area that I get. So this point is lambda and this point is lambda plus 2 pi. And these two areas will be equal. That is what this statement means. Remember, this can be in any place on the x-axis. The area remains the same. Of course, in this case, the area is 0. Here also, it doesn't matter where this is, from where to where it is. If the period is 2 pi, then it will be 0. Okay. So what happens to the coefficients? Formula of the coefficients. A naught is equal to 1 by pi times the integral from lambda to lambda plus 2 pi of f of x dx. A n will become 1 by pi times the integral from lambda to lambda plus 2 pi of f of x times cos nx dx. And similarly, bn will become 1 by pi times the integral from lambda to lambda plus 2 pi of f of x times sin nx dx. Keeping this in mind, let's figure out the Fourier series for this function, a piecewise function. Now here f of x is equal to 1 if x is between minus pi by 2 and pi by 2. And it is minus 1 if x is between pi by 2 and 3 pi by 2. Let's graph this. This is what we get. Okay, and we know f of lambda plus 2 pi is equal to f of lambda. And we know this is the Fourier series formula. Now let's figure out a naught. A naught we know is equal to 1 by pi times the integral of f of x dx in the given interval. So here, since it is piecewise, we take the integrals of each of them and add them in their respective intervals. So we have 1 by pi times the integral from minus pi by 2 to pi by 2 of 1 dx plus integral from pi by 2 to 3 pi by 2 of minus 1 dx. A naught is equal to 1 by pi times the integrals are pretty straightforward of 1 and minus 1 is x. Minus 1 is minus x. So x from, or rather x in this interval minus x in this interval. So a naught is equal to 1 by pi times. So for this first, we substitute pi by 2. So pi by 2 minus, now we substitute minus pi by 2. So minus pi by 2. Minus, now here again we substitute now 3 pi by 2 minus pi by 2. And when we simplify this, we get 1 by pi times pi minus pi, which is equal to 0. So a naught we don't have to bother about. if we look at an, we know the formula for this, an. So 1 by pi times the integral from minus pi by 2 to pi by 2 of 1 times cos nx dx plus the integral from pi by 2 to 3 pi by 2 of minus 1 times cos nx dx. Remember, integration by parts we have to do. When we differentiate 1, it will differentiate to 0, right? So the first term will be u as it is integral of cos nx, which is sin nx by n. Then minus derivative of 1 times integral of cos nx. So that will become 0. So we are left with only sin nx by n. In the interval minus pi by 2 to pi by 2. Minus, same way, integration by parts. We end up with sin nx by n in the interval pi by 2 to 3 pi by 2. Okay? So an becomes what? Here n and n are common in the denominator. So we take it out so that we can just focus on the numerators. Now sin nx. So first we substitute pi by 2. N times pi by 2 minus sin n times minus pi by 2 minus now sin n times 3 pi by 2 minus sin n times pi by 2. Now let's simplify it. 1 by n pi times, here you have sin n pi by 2. Sin minus x is equal to minus sin x. So minus minus becomes plus. So sin n pi by 2. Here minus times minus, when we open up the brackets, it will become plus. So sin n pi by 2. So we have 3 times sin n pi by 2 minus sin n 3 pi by 2. So an is this. And similarly, if we do it for bn, it will come out to 0. Let's apply these values in the Fourier's formula. F of x is equal to, now a naught is 0, bn is 0. So those two disappear. We are left with only the cost term. So we substitute that. Summation as n goes from 1 to infinity of 1 by n pi times 3 sin n pi by 2 minus sin n times 3 pi by 2 times cos nx. Now we have to figure out what the series is, the terms of the series. So before we can arrive at a general term, we need to figure out a few terms in the beginning. So let's start with T1. So that is n equal to 1. So when n equal to 1, 1 by pi times 3 sin pi by 2 minus sin 3 pi by 2 times cos x. And now we evaluate sin pi by 2, which is 1. 3 times 1 is 3 minus sin 3 pi by 2 is minus 1. So minus minus 1 becomes plus 1. So 3 plus 1, 4. So we end up with 4 by pi times cos x. Now the second term. So n equal to 2. So 1 by 2 pi times 3 times sine 2 times pi by 2. 2 cancel out pi. But sine pi is 0. So sine pi is 0. Here 2 cancel out. So 3 pi is also 0. So that means T2 is 0. T3 will give us minus 4 by 3 times pi times cos 3x. Fourth term will become 0. Fifth term will be 4 by 5 times pi times cos 5x. So I think now we have got the pattern. If we have not got the pattern, we have to, come out with additional terms. So here the series works out to f of x equal to 4 cos x by pi minus 4 cos 3x by 3 pi plus 4 cos 5x by 5 pi minus. So it will go to infinity. So this is the Fourier series for that piecewise function. Now let's look at the graph. This was the graph of the piecewise function in the interval minus pi by 2 to 3 pi by 2. Now, the Fourier series with just the first term being included will give us this. Let me also bring in this so that you can see what is the number of terms that we are looking at. So 1. Now 2 actually doesn't change anything, primarily because remember the second term was 0. Fourth term was 0. That means all the even terms will be 0. But the moment I say 3, graph changes, gets closer to the given function. 4, nothing changes, 0. 5, 6, nothing. 7, 8, nothing. 9. And like this, if we increase the number of terms, it gets closer and closer to that function. So if we take it to infinity, it will match or it will converge with that. So that was Fourier series for an interval which is not centered at 0. It was from an arbitrary point to another point which is 2 pi away from it. Again, let me remind you, there is a link to a PDF book which describes all these in detail. Please feel free to download it, refer to it, and if you think somebody else can also benefit from it, please do share. That's it for now. Bye.